Hello, and welcome to Cracking Pickles with R2. In this talk, we're going to be reverse engineering Python pickles and trying to figure out what they do. If we only focused on legitimate pickles that were created by the Python compiler, even ones you're trying to make weird but still using the compiler, this talk would be really easy. But it turns out there's all kinds of really weird obfuscation techniques that you can do when you start hand assembling pickles. And so we're going to play both sides of the fence, hand assembling really messed up pickles and then trying to find good ways of reverse engineering those pickles so that those tricks don't trip you up. My name's Dennis. I am a Radari contributor. In particular, I wrote the assembler and disassembler available in Radari for Python pickles. I also wrote a decompiler that is available as a plugin inside of Radari. So you can get it from r2pm. I think the decompiler is the only decompiler for Python pickles that supports 100% of the opcodes. So I've spent entirely too much time playing with Python pickles. I'm a security engineer at Doyensec, where I mostly focus on source code review, attempting to make source code act up in ways it's not supposed to. I have a degree in mathematics, and I used to be a professional magician. And so those three things together all kind of fit together. I really love just trickiness. And so Python pickles has a lot of trickiness, a lot of things that you wouldn't expect that it would have. And so there's a lot of fun to be had. What are pickles and why do we care? Pickles are just the serialization algorithm that's available in Python. This is the official documentation where it talks about it. And we can see right up front there's a giant warning label. And you know anything with a warning label this big has to be fun. Turns out getting code execution in pickles is trivial. 25 bytes you can run Who Am I? Pickles allow you to import os.system, that's what's going on here, and run whatever you want. Most people stop here. You already got code execution, that's what pen testers care about, we're done. But as reverse engineers, we're more interested in what is possible. We can get code execution, but what else can we do? How can we hide the fact that we got code execution? How would malware hide itself within a pickle file that is embedded in a Python file that's embedded in an exe? So here's one of my favorite pickles that I've ever written. I submitted this to PageStout and they were kind enough to include it in issue number 4. You should check out PageStout if you haven't. It's a hacker easy and there's a lot of good stuff in there. Let's look at it inside of an editor so we can have a bit more fun with it. Here we make a big pickle. This is pickles are just a binary string. This is broken up so that we can see the opcodes as comments on the right. We import the pickle library so that we can load this pickle, and we're going to load it and underscore load it. That is done right here. Here we see loads and underscore loads, and we print the results of them. They both return strings, and they should return the same string. We're loading the pickle and underscore loading the pickle. Both of those functions are supposed to do the exact same thing. The only difference between those is loads was implemented in C, and underscore loads was written in Python. The environment that they run in shouldn't dictate how they function. Of course, this wouldn't be a fun magic trick if they return the same thing. We also have we write the file to temp so that we can play with it with other tools. So let's run it. When we run the file, of course, the two results disagree. Loads produces magic, underscore loads produces more magic. If we look at the assembly real quick, here we see the stop instruction at the bottom. That instruction tells the pickle machine, which is a stack machine, to stop executing. The last thing that's on the stack is then returned. The last thing that's on the stack, we can see it right here, is the string magic. The opcode string magic, all it does is pushes the string, whatever argument it is, magic, onto the stack. Since that was the last thing pushed onto the stack, we know that we know the results of this function. We know how this should return. Not unless you can skip the stop instruction. And if you Google around, you'll find everyone says you can't skip instructions. There's no control flow inside of Python pickles. There should be no way that we reached down here where more magic occurs. Not unless I was lying about these instructions or something. We can validate those instructions with pickle tools, which is a disassembler. We could accept that pickle tools errors. R2 does work, and we can see that the instructions are just as we thought. We can also use the decompiler, and the decompiler even says we should return magic. So why is the underscore loads returning underscore magic? What's going on? How would we figure this out in a reverse engineering context where we're potentially dealing with malware? Some more fun facts about pickles before we get deep into it. Pickles are a very simple assembly language. We saw that earlier, but despite the simplicity of it, it gets very complicated, some of the obfuscation possibilities. So you will pretty much be a pickle expert at the end of this. There's not many opcodes, and many of those are repeats. Pickles have a lot of fun applications. They're used in a lot of places they really shouldn't be. Hugging Faces, for example, is where most people get into pickles because they host pickles as they host AI models as pickles. And so if you want to load an AI model, you have to trust that it's not malicious, that it won't run malicious code. So a lot of people think it's fun to get into pickles this way. I got into it from running into Python pickles as a save system from Pygames. A lot of Pygames, a Python game needs a means of saving its data, which is essentially serializing the Python object state of the game, and so pickles just works. So RenPy, for example, used that. That's the game engine for Doki Doki Literature Club, along with some 3,000 other games. So I notified them, and they now sign save files cryptographically using elliptic curve cryptography to warn you in case you're trying to load a pickle file that you yourself did not create in your video game. The cool part about that, other than adding malware to video games is a jerk move, but modding video games using the save state is pretty cool. And so any game that implements, any Pygame that implements Python pickles as a save system, you have a way to hook into the game and modify the game and share your modifications just by loading a save file. With the obfuscation techniques available, you can use this on red team engagements to try and avoid detection. And this is Python pickles are a common subject in CTF challenges because they're pretty simple but complex. The cool part, my favorite thing about pickles, like we saw before, is that there are many lies or half-truths to exploit in Python pickles, which is kind of the nature of how magic tricks work. So these are my favorite pickle half-truths and lies. So a lot of these are what you'll find regurgitated on the internet in various blog posts about how Python pickles work. But they are, at best, deceptive. At worst, they are absolutely wrong. Deceptive how? For example, Python pickle lacks a jump instruction. Yeah, that's true. Technically that is true. But we saw in the last pickle that we were able to grab the more magic string even though it occurred after the stop instruction. We effectively jumped over the stop instruction. We didn't use a jump instruction to jump, but we did jump. going to Google for a lot of this information, going to blog posts for a lot of this information, and Google AI is effectively trained on this blog posts, is not the best. Python pickles were never intended to be public. They're like how they work in detail. If you look at the older Python versions, there's comments that say that you shouldn't understand this stuff, that you should just use it. Because the opcodes aren't needed, we already have a compiler for you. Eventually, the basic ideas started leaking out as to what opcodes do, but those basic ideas don't always keep up with the implementation. The implementation may need to be tweaked slightly as things progress. Not documenting that implementation means that they can tweak it and not tell you, and as a result, a difference between the implementation and what blog posts and Google is regurgitating here means a great source of either bugs or obfuscation techniques. Here, Google's talking about the proto instruction. This is straight up a lie. At best, this is deceptive, but a lot of what this is really concerned with, a lot of what it's really talking about, really doesn't matter. What you do care about with the proto instruction is not mentioned here at all. So now that you're excited about Python pickle obfuscation, we need to start writing some pickles, assembling them by hand, and wreaking some havoc. So we need to learn the pickle basics. Rather than going through all the little nitty-gritty stuff and being boring, we're just going to throw r2 at it, write some stuff, and you'll learn as we go. So a lot of the rest of this talk is going to be from the terminal. So let's build our first assembly file. Well, I've already mostly done it for us. If you use a .asm extension, then it looks good enough in Vim. This is a very simple file. It puts two things on the stack by the time you hit the stop instruction. Only the last thing in the stack is ever returned. The stack will look like this just before the stop instruction. The big thing I want to show you is the mark instruction and how to put stuff inside of an object, or how to put stuff inside of a list, and inside of a container, let's say. There's two main ways to put something inside of a container. First, there's the things that we're putting in there. These are strings. There's just two different encodings of strings, string, bin string, and we want to put it in this empty dictionary. So the empty dictionary goes on the stack, put the two strings on the stack, and then the set item instruction grabs its set item from Python. It's the same idea. In this case, it's just grabbing the last two things on the stack and using that as an algorithm to set the item of the thing before that. So the stack is expected to have three things on it. The last one, the top of the stack, the top two elements of the stack are expected to be the key value pair. And the item below that on the stack is expected to be the dictionary, or something that supports set item. Mark is the other way that things are put into a dictionary. I'll show you tuple 2. Tuple is another way. Tuple 2 is another way things are put in the dictionary, or inside of a container-like object. Tuples can contain any number of elements. Tuple 2 just sucks up the last two things. Tuple 1 would take the last one thing from the stack. Tuple 3, the last three things. Tuple by itself, without a number, acts on a mark, the same as list. So this list down here is consuming everything on the stack until it runs into a mark. Mark, you can think of it as like an opening bracket pseudo object that is being put onto the stack. And everything, the list operation, the list opcode is consuming everything on the stack until it hits that opening element. That's not actually how it's implemented, and we'll see a bug in that later. But let's get into it. We have the file. We can assemble it with rasm2. Going to make sure that we specify that it's a pickle. If we do it without the -b, we just get the hex version. So let's put it into a file as raw binary. That means that we can detonate it with Python. And we get the result that we expected. We can also run it against pickle tools, which is going to attempt to disassemble it. It works, but pickle tools is not great. The offsets are not in hex like all the other tools. Instructions are expected to be capital always, which is annoying. And it's checking for stuff that it doesn't actually matter. We saw there was no error when pickle ran, but this ran an error when the stack contained an extra element on it. This as a form of obfuscation isn't very helpful because the entire pickle already printed. We can open it with r2con2024. Just make sure you specify architecture pickle, or you can change the architecture once you start with the environment. From there, the typical commands work. You can disassemble, use visual mode and make the colors pretty. If you have the pickle decompiler plugin, pickle deck, then it will, capital P can be used to decompile Python pickles. Like many Radari commands, the J flag is supported, which will produce JSON. And you can use the JSON interpreter in Radari to beautify it, and the pager even. Some other neat tricks, there's the Gron output, which gives you a greppable format so we can search for key. And if we wanted to patch key into something else inside of the pickle, we can grab here. That's the key value looked up through the JSON element. We get rid of the last element to go up once, and we get the object. The object has an offset. That's where the string key was defined, where we would want to patch. So we can seek to that location using a subcommand. So now we're at offset 3. Double check with disassembly. Set the file as writable. That way we can write the assembly string foo. String foo matches the same size as this, and so it shouldn't clobber anything. We can check. If you were going to clobber something, you can resize the file with the r command. We can further check that our patch worked by using PDP, the decompiler, from the start, and double check that it decompiled without error and that we see the result we desire. Or the that command from earlier, but from at offset 0. So that's the basic tooling system and how we will be reversing stuff later. The more malicious stuff in Pickle we'll be getting into next. Since we covered mark already, I'll show you a really simple, dumb thing. I don't really consider it a great obfuscation trick, but it'll get you thinking about how things can work. So here, this pickle puts a string onto the stack. The string's not really relevant. Puts a mark onto the stack, duplicates the mark Dupe is a instruction that takes the last element of the stack and puts it on the stack again, and then puts the int 42 on the stack and then stops. So really all this does is return 42. However, this instruction is invalid. You shouldn't be able to duplicate a mark. A mark isn't a real object. And the way Python actually implements this in practice, it doesn't push an item onto the stack. It takes the entire stack and hides it, takes it away, puts it on a stack of stacks, and then creates a new stack. That way you don't need to track, you don't need to search through the stack in order to find the next mark. You know the mark is there because that's the fake meta stack there of that size. So what happens when we try and duplicate a mark? The Fickling decompiler gets this wrong. It assumes that the result is 42. That's not completely wrong. That's kind of correct. In my decompiler, I raise an exception because the duplication can't grab the next element. And so at that point, I considered an invalid state, and I don't know how to continue from there, sadly. Python causes an error, unexpected mark found. When it tries to duplicate the mark, that's unexpected. And oddly, Pickle Tools gets through it fine and gets angry about there being extra stuff on the stack. Let's talk about globals. Globals are the dangerous opcodes. If you ask Google what the dangerous opcodes are, they'll say global and reduce. Global is what allows you, the global opcode allows you to grab any Python function, such as it's effectively import. You can think of it as import. And then reduce allows you to execute that function. Google is missing several other ways to grab global functions, though, and at least one other way of executing it. I claim these are the only 6 ways to get a global. I might be wrong. I'd love to be proven wrong, but I'm pretty confident in this. If you can find another way, you can bypass some tools. But for these 6 ways, I wish to validate my claim and introduce you to the Python source code for Pickle so that you can start validating your own claims that you have and checking stuff. So find class. This is the function that's used to look up globals. You can see it mentioned in the little documentation that's in the comments of the Python Pickle source code. If we go directly to that function, we see that it indeed looks up a global. It does it in one of 2 ways depending on what proto you're in. So that's what proto is actually used for. That's the only time proto is really used, is in this function. And it's used after the audit. So this is meant as a way to check what's going on in pickles, and this complicated stuff happens afterwards, so we'll get to play with that some to do bypasses there. Find class, if we cross-reference it, then we'll see all the instructions that use find class that look up a global. This dispatch is a dictionary that maps instructions to the handler. And this is the handler for that instruction. So the inst instruction, like I said before, uses find class. Similar, the global instruction uses find class. Stack global uses find class. It just gets the elements from stack pop, that's the virtual machine stack. And get extension uses find class, but that's not an opcode. That's not an instruction. That's a helper function used by these 3 instructions, load extension. And if you look closely at this, the key that is being passed comes from this registry, which looks up from a code, and that code comes from your instruction. So we're not supposed to be able to access this registry from a pickle, so we're going to. Now that you've seen the source, let's see how it works. This is global. It looks up the module, the function print from the module built-ins. Reduce is used to actually execute it, but reduce needs a tuple, and so since it's a stack, we have to put the tuple above. And since tuple needs something to put in the tuple, we use the string method 1. So this we'll call print method 1. Same with stack global. All the setup is the same. The only difference is how it's encoded. It accepts arguments on the stack, which means it's great for obfuscation, because if you can obfuscate how these strings got here, then you can potentially fool how the defense is attempting to catch this stuff. I'll show you an example of that next. Inst is another weird one. I've never seen a tool that, other than the built-in tools that use inst. Inst is very similar to global. It's parsed the same, but it automatically reduces. It automatically calls. It acts on a mark and puts the instructions or the arguments in between. ext. This is what I was talking about, I believe, with the ext. You need a global to use the global. ext looks up from a registry. So this poisons that registry. To get the registry, we need a global. From the global, we put an index in the global, and then put these strings as a tuple into that index. Set the item, and that's all you do. Now the registry is poisoned. That means when ext acts on the same number, I encoded them differently just to be mean, then what will be returned is an element from this index looked up through the find function and returned here. You then use the same tuple reduce system as before. So now I've already, let's look at it in Radari first. Decompiled, it looks like this. Print method 1, print method 2, print method 3. This one is the extension poisoning. It's setting up this object to be put the tuple as this key of the registry, of the inverted registry. And last is we get that element from the inverted registry and call that element here. So let's run it in Python, and we get all the prints as expected. In pickling, we get an error because the inst opcode is not supported. Now, I'm not trying to beat up on pickling. Pickling is a great tool, and that's why I'm showing it, and that's why I'm showing these obfuscation techniques against it. Another tool made the same mistake. This was pickle scan. I sent this is much more dangerous though, because pickle scan is purposely trying to find malicious pickles, and this bypassed, using the inst instruction, completely bypassed this malicious detection without even a warning, without a crash. They were very quick to fix it though, so good job to them. While we're talking about pickle scan, I found a second bypass in pickle scan a while back it's even more interesting. I don't think I've talked about it yet, but pickles have a memo. Memos let you duplicate an item from the stack and put it into the memo at an arbitrary index. It has to be an integer assigned index. So, for example, this puts OS onto the stack, and this puts that string as memo entry 0. So memo 0 is OS. Similar, we put that as entry 1 to be system. The problem PickleScan had was they did not parse bin put, because the modern way to do it is with memoize. So memoize was parsed, and so PickleScan thought that this entry was memo 0 and this entry is in memo 1. So when we go to get something that might be dangerous, using strings from the memo, PickleScan assumed that it was these safe strings when we had already loaded a couple things in there earlier. So this was the second bypass I found. This is a lot trickier to figure out how to fix, but they did a great job at fixing this also. So this obfuscation trick is what I used inside of the schizophrenic pickle in order to hide some of the assembly from pickle tools. If we run pickle tools on out.pick, we see new true, bin put, memoize, and that's it. It errors before it prints the rest of the information. There is a way to get around this with pickle tools, importing it and doing some stuff, but if we look at the same, also importantly, we can detonate that file and it does work. Looking at this in Readari, all that's happening is we're putting true on the stack, saving that value to the memo in entry 1, and then we save it to the memo again. Memoize doesn't actually save to the first empty spot. It takes the memo, takes the length of the memo, and sets the top of the stack according to the length of the memo. Since the length of the memo is 1, it sets entry 1 of the memo, rather than entry 0, the first open slot, to new true, where new true already is. Pickle Tools, for some reason, doesn't like that and thinks that it should stop and die an error there before it gets to this string that says something dangerous is happening. So using that trick, you can make it just a little bit more annoying to try and disassemble something with Pickle Tools. Okay, it's time to break my own tool. If you look at the assembly for this code, you'll see name mapping up top. Decompilation shows name mapping down here. This was a design decision that I regret, and I'll show why. This pop instruction, this was my original reasoning. Pop instructions are very rarely used by a pickle. Pop essentially takes the top of the stack and just deletes whatever is there, removing it from existence. This is very useful for malware. There's some automated tools that will automate inserting a malicious pickle at an arbitrary location and then popping the results of the results of that effect from the stack so that the legitimate pickle can continue without the stack being modified. So pop is something you should know about if you're looking for malicious pickles. Pop rarely occurs in legitimate pickles because why would you put something on the stack just to delete it? So there's two flavors of pop, pop and pop mark. Pop mark pops everything up to the mark. A more subtle and difficult thing to find for injected code is set item. Here's an example of set item here. Set item is the same as what you would expect in Python. It's setting the element of a dictionary. But if you set the element of a dictionary that already exists, you can clobber it out of existence. So that's a great way of you insert your malicious code. It causes a new item on the stack, but you set that item, and then a legitimate set item that follows clobbers your malicious item out of existence. At any rate, due to that design decision, due to that idea, I wanted all pops to be very explicit inside of the decompilation. As a result, though, it puts this code down here when it should really be up here. Here you see the 54 is the offset where it occurs. 55 or 59 is where the code starts executing. This code here is poisoning the state of the pickle machine, and so the rest of this code, it changes how the rest of this code should be interpreted. What's happening is the name mapping exists in order to translate Python 2 pickles from the Python version 2 to Python 3, because some names have changed. Underscore underscore built-in has become built-ins. As a result, when Python pickle goes to look up a global, it uses proto to check whether it should consult the name mapping. Proto version 4 is Python 3, we don't need the name mapping. Proto version 2 is Python 2, we do need the name mapping, and so we look up built-ins print and find os.system. If we look at this in Fickling, they do better in the sense that the poisoning is seen early. And anytime you see a pickle import something that has to do with pickles, you know it's doing something weird. So this should set off alarm bells. They don't indicate how print was discovered and what proto version was used, and so if you don't pay enough attention to this stuff, you might think that this is a legitimate print. If we run it, we can see that indeed whoami is returned because it is printed, and then whoami is executed as system also, and the return code from system is returned. Here's another fun one. This is a pickle that unpickles to itself. What that means, it's called a quine. When you load this pickle, you get an element returned, and those two things will be the same. So a pickle that returns itself. More interesting though is you can use this to loop. Once we have a copy of the pickle, we can just call pickle.loads on that pickle and execute that copy again, which will run the same pickle and call pickle.loads again. So this pickle will attempt to infinitely recurse on itself, loading itself every time. It also, this is where the load occurs. It also attempts to print itself every time. Here. What's interesting about this too is that since it never returns, there is no reason for a stop instruction. The Python doesn't look ahead to verify that a stop instruction exists. It's not strictly necessary. So this is one of the ways a pickle can avoid using a stop instruction. The other way is the pickle can just error, and if the error is caught, then it doesn't need a stop instruction. It will execute up until it hits the end of the pickle. So let's see this in action. Here is the same pickle printing itself over and over each time until it hits the maximum recursion depth. Since we're talking about quines, it reminds us of self-reference. Mathematicians love or hate self-reference, and we can use self-reference inside of our pickle. Unlike JSON, after we create an array or a list in Python, we can reference that list and append to it. So we can duplicate a list, append itself to itself, and then print it. That's done here. This syntax is not valid Python, but you get the idea of what's happening. If we run it in Python, it's perfectly valid and executes without error. Pickle tools shows exactly what's going on. Empty list, we put the list in the memo, we get the list, and then we append the list to itself. Pickling, when it attempts to print the list, it realizes there's a list inside of it, and so it tries to print that list. But when it tries to print that list, it needs to print the list inside of it, and it infinitely recurses until the max recursion limit has been reached. So this next obfuscation trick is really a bug inside of my decompiler. I'm going to show you a version that I fixed, but much more complicated versions exist that I do think cause my decompiler to get off track. And those versions just aren't, it's not worth it to go into the details of that. I'll show you the basic version. So this is the most basic example. You make a list and append old to it and print it. Then you put that in the memo so that you can append new to the list and print it again. It sounds simple if you think of pickles as a programming language, but pickles really are supposed to be a serialization algorithm. JSON can't do this. JSON can't make an array, finish the array, and later come back and change it, or use the array to construct an object and then change the original array after the object was constructed. So from a decompiler perspective, this wasn't something that I had considered would happen. And as a result, I was not properly keeping track of when this object changed. Pickling runs into the same problem. It prints old and new together. It doesn't keep track of the fact that old is only present old is present by itself in the first print, that new should not be here. The second print is, of course, correct. R2, if I run it with the quick out flag, I get the same error that Pickling gets. I create the list and print the same list 2 times. If I run it without the Q flag, I do get it correct. But you have to understand there's many versions of this, not just in lists, but in dictionaries and in objects that implement dictionary or list-like methods. Also, this is a recursive problem. That's why the quick flag runs faster. And this is why if you use the JSON output, you might see a pie split. Here we have the pie list. We have the 2 elements, new and old, and between them, I've marked this list as having been used by a reduce at this location. And as a result, you can piece together what this list was at a given point in time. If you see this pie split inside of JSON using like r2 pipe, for example, that's what it's used for, and it might indicate that the pickle is hand assembled or doing something awfully weird. So this might be my new favorite obfuscation technique. I'm not sure. The next one is the last one, and it's kind of a toss-up. This is the newest obfuscation technique, though. You can always pair any of these obfuscation techniques together, of course, but let's just look at it. This is what the pickle looks like in Radari, and the thing that stands out is there is an awful lot of appends. There are 200 appends at the end of this pickle, and then a stop instruction. There are not enough instructions to make enough elements on the stack that 200 appends would work. Every append takes 2 elements and turns it into 1 element. Takes the thing that is going to be, the top of the stack should be the thing that is to be appended. The thing before it should be what will be appended to. So we would need at least 201 elements on the stack in order for those appends to work, naively speaking. So if we use the decompiler, it breaks and it does not reach the end of those appends. And so we could add any other instructions to the end of those appends, something malicious, for example, and my decompiler will never reach that point. It'll never get to the point where it's showing you the malicious code. Fickling messes up also, and so does pickle tools. And this isn't even using the memo trick I showed before. This is also getting angry because of the appends. There's not enough things on the stack to append. If we run Python pickle on it to detonate it, it gets angry, but only because it's using load. If instead we use underscore load, which this basic script does, we get the answer 42. So what's happening? How are those appends not causing an error inside of Python pickle? Radari is the best tool to use for this, and the decompiler is the best way to look at it. This decompilation is ugly enough that you might want to start renaming these variables. You can do that by first using the F when you decompile. That will make all the flags appear. They're all prepended with pick. And so then you can rename a flag according to what you think it should be named. And when you decompile again, that new name will be used in the decompilation, which will help clean things up a little bit. Get adder from built-ins is usually kind of an indication that something bad is happening, especially if you use a bunch of them. Python pickles are not allowed to, the goal of a pickle is to build an item, not take it apart. And so there's probably not a good reason to be getting that attribute of some object and burrowing down into it from within a pickle. At that point, you're not building, you're narrowing down. And in this case, what's happening is inspect is being used. Inspect allows introspection in Python. Stack from introspection is being used, and the stack element 0 is being used. That function corresponds to the pickle machine. So we're getting into the attributes and variables of the pickle machine that's running the pickle as the pickle is actually running. If you follow this down, frame, flocals, self is referring to the self element of that class, which contains stack, as in the stack that we saw in the source code earlier. We're able to get the stack from the stack machine and put it on its own stack. At that point, we can append to the stack. And when we append to the stack, what we're doing, so we put 42 on the stack, underneath the stack. So the stack contains itself and 42. When we run append, we're taking 42, the top of the stack, off and appending it to the previous item on the stack. What's the previous item on the stack? That's the stack itself. And so the result is we get the stack containing the stack and 42 again. We can append again, take the 42 out of the stack and just put it right back in. Append has effectively become a NOP instruction. Attempting to figure that out inside of a decompiler is, you need a Python interpreter. You need a Python interpreter to figure out that all of this corresponds to just the stack itself. However, if you're a reverse engineer and you ever see inspect being pulled inside of a pickle, that's almost surely one of the worst things that could show up inside of a pickle. So here's my final trick, the schizophrenic pickle that I've been hinting at this entire time. This is it decomiled and disassembled. the global here is loading from pickle, so you know it's going to be fun. The unpickler, that's from the Python unpickler, .dispatch. If you remember, dispatch is a mapping of opcode to opcode handler. It's just a dictionary, and so we can use set item on this. What's happening is the dispatch table, the opcode handler for 85, which if you do some RASM stuff, you can find out that it's short bin string. 55 in hex is 85. The opcode handler for 55 is being set to the is clobbering the opcode handler for 83. That is S, which is for string. This is the set item that causes the poisoning of the opcode handler and changes the assembly instruction that we're using. After that, all string instructions are no longer handled by the string handler. They're handled by the short bin string. So we can patch this to short bin string to see what should be here. Short bin string is the same as string. It creates a string, but it's encoded differently. String is new line terminated. You can see the new line termination is right here, and it has to be surrounded by quotes. Short bin string uses the first byte afterwards to indicate length. Since 27 hex is longer than this 0A, we jump over that 0A effectively. We can turn the write cache on. That way we can write the 55 byte to where 53 used to be, and Radari will treat this as a new instruction, as short bin string. This does suck up more of the stuff after it, like we expected, and then here we have an error, but that's because it's 53 again. If we go to that location, 53 is no good. We need to write hex again. Now it's short bin string more magic, followed by the stop command. Completely decompiled, we get what we'd expect for the second version of the pickle. This only affects the Python implementation because Python's implementation is the only one that uses this dispatch handler. Further, you should keep in mind this only rewrites one opcode. You can rewrite the entire table and use completely new opcodes. This is a real pain to have to patch and keep patching if you keep changing the opcodes throughout the instruction set. Also, if you have a web server that's vulnerable to pickle deserialization, you can poison this opcode handler in one pickle, wait a week. As long as the server's still up, it's still poisoned. It's still using the loads method for all normal pickles, but you can send a pickle that calls _load itself, and that _load will use the poisoned dispatch opcode table and attempting to go back in logs over those weeks in order to find the poisoned version of the assembly language that needs to be applied and decompiled and all that is nasty. Just don't deserialize pickles. So to wrap up, if you are trying to make Python pickles safe, good luck. And if you have any questions, feel free to reach out to me at these places. I hope you enjoy r2con.